Alright, another draft physics video production. Yeah. Anyway, so these two guys I could confuse, this Stephen Bro guy and this Richie, right? I think that's it. Me and names is so bad. There we go. Yeah, Richie. Robert. So, got it wrong already. Bob. And such. Anyway, so he's made another video that's, not exactly. So I just figure I'll go through it and point out how it's not exactly what I'm saying, kind of thing. I mean, you can grab pieces of what I'm saying, and that's fine. But I would still think that we disagree more than we agree, but who knows. So we'll play a little of this, and yeah, it's worth commenting on because it brings up different subjects. So I think it's all, it seems reasonable for people to interact in this kind of way. So I'm going to do what seems reasonable.
G'day viewers.
Good day.
Just a bit about neutrons. Just give it.
I thought he was English, but he's Australian. But some of the English sound Australian, some of the Australians sound English. So it's close enough.
A background. It's probably like chapter 3 in the book, but we'll just get it out of the way. You're looking there, it says mean life of 881.5 seconds plus or minus 1.5 seconds.
All right, so he's worried about neutron decay, which sort of doesn't mean anything, but that's obviously when they've broken atoms into pieces, and they basically, they can pull off the electrons and the protons because they're charged, and so they're left with a clump of crap left over, and they decide how long it takes for the clump of crap to fall apart because it's not an atom anymore. Clearly neutrons, I think the physicists would agree, are quite, they have an eternal life as long as the atom is intact. And it's only when the atom is broken, or the arrangement, the pressure, is destroyed, that the neutron falls apart. So I don't think this half-life means much in terms of a real thing, because it's not the real condition of a neutron. So the fact that they fall apart outside of atoms isn't such a great surprise.
Yeah, that's the mean half-life. At the upper end of the bell curve, you could have, you could have stable neutrons living quite easily twice that.
Well, clearly, I think if you had neutrons in something like a neutron star, you could argue they could live 1,000,000 times that, or 1,000,000,000,000 times that. So this sort of gets to the main theme of this whole conversation, which is, he's saying like high energy to low energy, and it's the notion's got to be changed to pressure. It's just all about pressure, and pressure's all about push. So ultimately, all you're saying is, where's there high pressure and where's there's low pressure? Where are the pushes? And that's it. But like I said, analyzing atoms and trying to pick all this, all these little parts, these neutrinos, the this, the that, it's all doesn't mean anything in my opinion. It doesn't add up to anything. 99% of the function of the universe is substance, matter bits, stuff in atoms mostly, interacting with force bits, stuff like photons. And there really isn't any role for neutrinos and desinos and mezinos and desinos. They're just not relevant. Maybe they are constituent parts, but who cares? The constituent parts don't do anything as far as we can tell. Maybe they're integral to the function of the electron, or function of the proton, or the function of the neutron. But again, we already have isolated the fundamental function, which is the pressure of the force imposing momentum on the matter. The pressure of the force imposing momentum on matter. That's all we really need to know about the universe.
Even longer. We're just looking at a neutron contains a proton and an electron, and there's a little bit left over, and that's
So again, this thing too, like somehow they know what leftover bits are. I would argue clearly that if you have an electron and a proton, that there's going to be some interaction between them, just in the fact that the thing, we know it's decaying, so we know in some extent it's going to change through this decay process. Something happens to it for that 14 minutes and 42 seconds. So something's happening to the neutron through that period of time, and it's not that the proton or the electron's changing. Essentially the energy between them is changing. So maybe at the point where they actually do fall apart, there is no leftover energy because it already dissipated.
Usually, as you see I've written there, an electron neutrino or an electron antineutrino.
So you can believe in these things if you want to, I guess, but I'm going to argue that until they have some real evidence of this stuff, why should I believe in it? It's like dark matter. This stuff isn't any more well evidenced than dark matter. It's merely deduced that this stuff exists because they do have remainders or leftovers, because there is something wrong with their current perception of how it works, and they have to explain, they have to account for the little extra bits here and there. So because they think galaxies are contracting rather than expanding, they think they have to invent dark matter to fix a gravity problem. Where if they thought galaxies were expanding, then they would expect the stars to be moving too fast on the outside because they're leaving. See, I mean, it's just a simple thing. So if they've made one wrong assumption, antineutrinos disappear or neutrinos disappear because they no longer have a wrong assumption that they're basing the existence on. They don't have cloud chamber tracings of these particles. They don't have hard evidence of their existence. They're dark matter. They're imagined solutions. They're not real solutions. They're not real evidenced mechanisms.
And a gamma ray photon in those combinations, you can have there's some forbidden combinations there, but there's some absolutely proven. Look, I don't have to do the experiment.
Absolutely proven. Again, those are just such dangerous words in this environment, frankly. I'm just saying that this is a trial. I don't think somebody can come in and say, I've absolutely proven that that's his jacket. Even though there's 5 million of those jackets in the United States, and I can absolutely prove it's his, and I don't have any reason to believe it's his other than there's a photograph with him wearing a similar jacket. You know what I'm saying? That's not absolute proof. So everybody throws these words around like they've proven something. They haven't proven anything. I mean, yes, some things have been proven, but I just mean they've used the word. They've cried wolf. They've cried proof so many times when they haven't got grounds for using those words. Like we've proven it's a wave. They haven't done that.
Got the results of the experiments. You can Google it yourself and read up. But neutrons are very important in the whole symmetry, asymmetry argument. If you're going to argue
Yeah, well, okay, I'll do a little drawing here just to make this clear what I'm arguing, that this isn't that complicated, and we don't need to, I don't think there's any need to strangle ourselves looking for every single bit of crap that might have something to do with an atom. So, I mean, the basic idea is you have the two essential ingredients are the nucleus and the stuff that's on the outside, the electrons. And we know why they're attracted, and we know the electrons are repulsive to each other. And so we can, from that model alone, we can create tension in an atom. That is, we can create a mechanism where the electron is being prevented from crashing into the proton because of the tension between the electrons. And that's true even if we put them at odd angles to each other. We can create a mechanism that prevents them from crashing into each other based on how we configure an atom. Well, the key thing to the nucleus, so the idea is the nucleus has a bunch of these protons in it that are theoretically much too close to each other. Their repulsion to each other should be making it impossible for them to be this close. And that's the strong force in physics. But what the key ingredient is the neutron. So if I put a proton-electron pair in here, then I completely change the balance of power inside this nucleus, in the sense that, as I pointed out, an electron and a proton have this feature of disposing of each other's reflective energy. So now you don't have reflections back and forth between the protons because it's been mitigated by the electron's existence between them. So all I have to do is create these pairs. A neutron-proton pair essentially creates a configuration, something like this. So it doesn't matter which one you call the neutron, which one you call the independent proton, but we'll put an X on the independent proton. And so this is your neutron, this is your proton. So as a pairing, it's quite obvious what's going to happen here, in my opinion. It's quite obvious that instead of having two protons with ping pong paddles, if you thought of them with the ping pong balls bouncing back and forth and the energy getting stronger as they get closer, all of this red stuff is going to leak out of this electron. And so now there can't be any reflections between the two protons because it leaks out of the electron. And so now you can get these protons really close to each other because you have this catalyst here to take care of the energy problem, get rid of those reflections. So that's what's creating the illusion of a strong force. So in fact, the force inside the nucleus isn't really a strong force, it's the absence of force. It's getting force out of the nucleus, it's pushing pressure out of it. So it's an absence of pressure, and now the external pressure is what's pushing the thing together. So it's, again, they've got it backwards. The strong force isn't inside the nucleus. The strong force is in the field pushing in. And when you take the pressure out of the inside, the equalizing pressure, then the thing it collapses quite easily. So that's my argument of the role of a neutron, is that it's fundamental to keeping protons close together.
The universal field theory, which I think Gary from DraftScience, I think he's probably pretty close there with what he's come up with. After I've done some analysis, I listen to everybody. I listen to the Electric Universe people and Eric Verlint with his amazing theory, but his isn't even complete yet. It's pretty good if you want to read it. Yeah, the old neutron. It's got a little bit more than just a proton electron, and that tiny little bit of difference changes the whole outlook of the picture that we form of the...
yeah, I say it shouldn't. I'd say that difference doesn't matter. The real magic of the neutron is the fact that it is a electron and a proton, which is the dipole, and besides being just a dipole in terms of charge, not a neutron. See, they're making it out to be neutral when no, it's not really. It's only neutral in the sense that it's got both poles. It's the true first magnet. Okay, it's the smallest magnet you can have is the neutron. So they're only seeing it as neutral because it's got both poles. It's got this. The plus charge is annihilating the minus charge, and the fact is we can't get close enough to that dipole. Like any dipole, from a distance, is going to look like nothing. Because from a distance, this R cubed rule comes to an effect, and it's not an R cubed rule because of any other reason than the dilution of the two colors. Okay, from a distance you don't see red and blue anymore, you just see the violet or whatever, you see the mixture again. All right, so the thing is we never can get close enough to a neutron to see this polarity, but it's there. From a distance can't see it. It's as neutral, okay, as something that would be neutral, but it's not neutral up close. It's a dipole. It's the smallest magnet.
Universe at a quantum mechanical level, and what I think DraftScience is postulating there could have major implications, and we'll see some of the results. I've done some working out, and I've done a bit of reading, and you know, it's mainly mental thought. You've got to really put some thought in and say, well...
Yes, I have drawn 7 million pictures in the last 7 years. A ton of drawings and modeling and modeling and modeling and modeling. And you have to go through a lot of crap to figure out what doesn't work before you can figure out what does work.
Does this obey the basic laws of physics, or does it not? And I think these primordial...
No, but the point to make is all you want to do is fit the evidence. So we have a ton of little pieces of evidence, and you just want to come up with a model that works for all the evidence that exists.
Force bits that Gary talks about, I think they existed before even quarks existed, before the quark.
So this is quarks, quarks. Subtle difference, but you know. Anyway, I hate the word. I just hate the concept, hate the whole thing. But I sort of like the fact that there is he's found a connection. See, I wouldn't even have bothered looking for it. But to this idea of how you can end up with a spin 1.5 and a spin 2/3 and all these weird numbers they're coming up with for spin numbers, when the spin number might just be a magnitude number of adding, you know, red to green. All right, so you can end up with odd numbers. So if I have 3 items, then I'm going to have a plus half, so to speak, half strength, because I've neutralized. Yeah, well, that's the tricky part, because you're just talking about it being in a condensed state. So again, we're back to this dipole. Well, I can make a dipole, but if I put another red thing really close, then I have some kind of tripole, right? So if I have a positive piece of energy and a negative piece of energy and then another piece of positive energy very close together, well, sure, what are you going to actually see? You're not going to see a full red charge left over. These two won't just neutralize each other, because it'll be more like the red is stronger but not completely stronger, and especially up close it's going to look like a half. I mean, 3, the odd numbers would end up giving you half integers. So anyway, that sort of, you know, and so that sort of fits into what quarks are. So quarks might be physics's representation of the energy they get back from a system they agitate. And so they get back this little bit of extra energy and they call it a quark. But it's just energy, it's just the force bits.
You know, so many billionths of a second after the what they call the Big Bang.
So again, I don't know, that whole conversation to me is just a waste of time. It's all speculation, very little hard evidence. They have just little tiny shreds. You got a little bit of redshift, you got a little bit of I don't even know what else they have besides redshift. They don't have much that they're making this whole thing out of. So I'm just saying there's so little evidence of it, and I just don't see it as a point, as a very purposeful conversation to sit there and speculate about how the first electron was born. I just don't think we're ready for that conversation.
That's a whole nother story, you know.
And by we, I mean the entire human mind. There's just not enough information.
They can't understand the Big Bang. Well, I've got my own version of the Big Bang that fits right in with all this, and I would like to say that it's my opinion, after a lot of thought over many years, that the actual Big Bang is one case where a singularity did occur, and it was...
Yeah, I don't know how you could possibly make any statements about singularities even being possible, what the hell they would be made out of. Again, by my deduction, I would argue there's pressure in the universe, and there's only so much of it. You can't make an infinite amount of pressure, so what's the conversation for? What's the use of it? Forget about it.
Singularity, I think it was a singularity that developed into a major rip. But that's another theory for another video a long time.
Yeah, all this major rip stuff, all this huge expansion thing, in a millisecond the universe got 1 trillion times bigger. I just think all that stuff just sounds like magic to me, so I just don't see any point in going there. The universe seems pretty consistent in terms of its function. You know, it doesn't have any pockets of complete aberration. I mean, it's all kind of lumpy and, you know, as you would expect. So, you know, I just don't see why everybody thinks they're going to find something in this puddle of vomit that's, interesting.
Sure. And a lot of you won't like the answers that I've come up with, so I'm prepared to argue with certain people.
Well, yeah, I'm just saying I am totally disinterested, so I'm just saying I'm not going to argue origins of the universe. It's just, there's just no reason for me to think I could compile enough evidence from what we have to say what happened a trillion years ago, a billion years ago, 30 billion, okay, whatever. I just don't think there's anything there. To draw deductions about what galaxies might be doing in terms of how they're evolving, I think that we can do that. We can sort of notice that the galaxies get smaller and brighter the further away in time they are. So there seems to be an indication that galaxies are falling apart, not collapsing. So I think I can make that argument.
I'm not going to argue with everybody. I don't have the time. I'm just going to put it out there, and I'll show you what I've come up with and why it works. And it works so well once you start. It's like when you do something.
Yeah, see, I didn't see the working part in here too much. I love the colors, of course, but it's just a wrong representation in a sense. So let's jump to my website for comparison. So he's taking the traditional lines as if they mean something, and as I've tried to point out, they mean nothing. They're just a byproduct of what happens to compass needles. So when you go to detect how much energy there is, this is the energy profile you get. And all it's really telling you is that there's an imbalance. You get a lot more red energy here and a lot more black energy here. And so the magnet lines up north-south, because it's the strength of the low pressure is very strong, and they're pushed this way, vertical. And then as you start to go away, there's more and more red hitting the object, and so now it's bending to balance to the red to the black, the red to the black, and as you go around it starts balancing more and more, and then when you're perfectly across from the magnet you have exactly the opposite alignment, the north to the south to the north. And as I've pointed out, these lines are all opposite magnets, so he's sort of implying that they're the same magnet because he's got the black in the lines. No, they're opposite. Those iron filings are creating an opposite magnet, opposite polarity. That's why it's lining up. The compass needles line up opposite, and and the reason why they have distance between them is merely because they're all the same. They're all opposite the primary magnet. So all the lines are doing exactly the opposite of the primary magnet, and they're repelling each other. So they're attracted to the main magnet, but they're repelling each other, and that creates the lines. That's it. There's nothing else happening. There's no circuit, no connections, no anything. They're just little pieces of crap that happen to line up in a certain position, and that's it, because the field is balanced. And again, if you didn't have something preventing them from moving, the friction of the paper or whatever you put the iron filings on, they would tend to just want to go right into the magnet. If they were in free space or in a liquid, you won't get these really nice lines. You get some of that, but it'll deteriorate because it'll just keep moving, okay, and eventually stick to the magnet, because that's what it really is doing. It's an opposite magnet. It's going to move towards the magnet eventually, and so you can only get these lines for a short period of time in a fluid.
State physics, you got to take into consideration hole flow as well as electron flow. So you've got these moving holes moving in one.
All right, so hole flow. I mean, it's a kind of surprising you just throw out a word like hole flow, like somebody's supposed to know what that means. I mean, clearly you might have your own audience who've heard this stuff before, so I certainly say things, bits, and all kinds of stuff in videos that obviously if somebody's a first-time viewer, they're not going to get that. And maybe I should start every video by pointing out if you're a first-time viewer, blah, 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 but that seems like a terrible imposition. Maybe I'll do it at the end of every video, and then people can just not watch the end, because I know it's just going to be the same speech about what a first-time viewer should understand about these videos. That might be a thing to do, actually. So anyway, all right, to the website just quickly. So this is what I would argue is the right image of to understand what a magnet's doing. It's radiating force, straight line force, little straight lines of photons, real photons, not virtual photons, real photons, not visible ones, invisible. They don't have a frequency. They're bits of energy, bits of momentum. And they have the two polarities of electron strong and proton strong. That is, one energy pushes on protons and one energy pushes on electrons. And that's the structure of the magnet. And the magnet essentially becomes a reflector. So the outside of the magnet is reflecting the force it's excreting. And that means that any red force that hits this part of the red magnet, it reflects, which is an absorption, but it's a reflection in terms of what the world will see is the same force coming right back at it. And the same with the black. And obviously when you put two magnets of the same polarity lined up, they're going to get a bunch of energy. It's going to just keep reflecting between them like ping pong paddles. The closer I bring the magnets, the faster that stuff is going to be going back and forth, the more impacts per second, which means the more momentum per second. And that's the repulsive pressure you feel. But the lines are just arbitrary. They're just a manifestation of the creation of this the end result field. Very unmixed at the ends, very mixed in the middle, and that's the nature of the field. And again, the iron filings are just creating a secondary magnet that's the opposite polarity to the primary magnet, and every opposite magnet is just repelling the one next to it, and that's why there's distance between them. That's it. No more, you don't need to make it any more complicated than that. Mixed force comes in, the magnet segregates it, the red stuff comes out one end, the black stuff comes out the other end, and that's it. Complete story.
And electron charge carriers moving in the other, and that's pretty amazing. So let's just have a microscopic view at DraftScience's postulations and how he thinks things work, and I'll give you my interpretation, whether I'm right or wrong, I don't care. This is just what I've worked out, and what he's saying is let's just deal with colours. I would like to have red and blue, that's the traditional magnet colours, but and I apologise for the phone held video because I don't have a HD video camera. I spend my money on.
Yes, I understand, but I guess you could tape it to something, or make some kind of more stable stand for it. I mean, I don't have this. I have a scope cam, from China, $5. That's this cam. This cam is it's a little scope cam, which they're really very nice in the sense that they really do macro quite well. So I really want to try to do some experiments with their macro capacity because it's really quite good for a $5 camera. So, but anyway. But yes, I did. This was my old setup. So I had a little clip. Okay, clips on things, and then I taped the webcam to an old light that wasn't working too well. So just to make it so it didn't move around and jitter and do all that crap. So just saying.
It's like a lot of money on experiments, as you'll see. Some pretty crazy ones coming up. But we'll look at the magnet, and Gary says there's two types of force bits. Yeah, it's a great concept when you take it. When you step back and look at the big picture.
Yes, I think it's also, when I realized it, I said, this just opens all the doors. Because now you can explain what a charge is. You can't explain charge until you do this. It's just not possible, I don't think. Because I've tried everything. All this stupid spinning crap. If it's going clockwise, it's positive. Well, how does that work in 3 dimensions? That falls apart. That can't work. Then I have to make all the atoms 2-dimensional. And then the atoms are, Well, that's still not going to work because it'd still be able to turn them into positive or negative based on which way they were spinning and which way I looked at them. Blah, 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 blah. You know, I couldn't make anything out of charge. It just kept being dead ends. And when I realized all I have to do is make a force filter, when I realized, I don't know, I think that's the way it happened, is I looked at the magnet and I said, what the fuck is it doing? And I said, well, what I know it's not doing is it's not making light because it's not getting any lighter. It's not losing any energy, right? There's no theory that says there's a half-life to a magnet, right? I mean, it's a magnet till it's not a magnet anymore, right? Till you whack it with a hammer or fuck it up some way, and that's not really destroying its ability to be a magnet. It's just destroying the fact that it's magnetized at the moment. But its potential is still there. So clearly, what it's doing can't be coming from inside of it. And that's when I realized it has to be interpreting an external force. And I said, of course, it's the gravity force. It's gravity that it's interpreting. And gravity's polarized. That's all there is to it. And yes, it doesn't need the polarization when it's doing gravity because everything's mixed up. There's nothing magnetic. There's no magnets, so it's just gravity. But as soon as you make it into a filter, then you really magnify the capacity of the force to affect things. You know, because then you're segregating a very differential force. A force that has a very different effect on a proton than it does on an electron. So yeah, just open the door. Bingo, it all fits now. I don't know why I'm having a hard time explaining that, but I guess I'm having a hard time because there are people like the Hilster loonies who sit there and think their charge is a nothing. I can just forget about its existence. I don't have to explain it. When it's like the most glaring function in the known universe. It's even the fact that it's like everybody's notion of an atom. They're using this gravitational model. They're not using a magnetic model. They'll say that it's magnetic. They'll say that charge is making it work, but they won't account for how it's doing it. That the charge actually matters. That's the function. It's all held by magnetic tension. It doesn't need orbits. It doesn't need all this other crap. So yeah, just huge. Fog gone. It's like just wiping the windshield, the dirty, stinking, and it's just, whoa, look at the world. Holy shit. I wasn't seeing anything because I had this blinder, this fog, this bullshit in front of me that once you explain charge, you got the game. You're rolling fast.
So we've got the red. Now they come out of this red end and they try to come out straight, but what happens is
no sorry, you just made a mistake. No, they try to come out straight and they do come out straight, and if there's a magnet in the way, then the magnet will turn based on the strength of the force, but that's it. The force isn't stopped. It isn't doing any of that kind of crap. I mean, clearly when there's energy used to move the magnet, so obviously those little bits of force are being used to move the magnet, but we know that there's always equilibrium, and the magnet moving, it will give back the energy it used to move, so it's not going to keep it very long.
So they're all the same. Well, let's use electric charge. They're not. It's a magnetic field, but you've got to have the electric charge analogy. What they're doing is,
see, it's not an analogy. Electric charge is just the monopole version of the dipole magnetism. So again, I'll say it again. The electron and the proton are the magnetic monopoles. And the neutron is the smallest dipole.
Pushing away from each other. And the first thing they're doing is they're looking for their mate, for the opposite charge.
No, it's always a push force, and clearly, so again, he's thinking these stupid field lines are representing something that the force is doing. No, that's just what compass needles do when you put them in the field of the force. They line up in a certain way, and it's going to be completely proportional to the strength of the force. And that's what you see, is completely proportional to the strength of the force. The lines are very close together at the red and the black end, and then they get further apart in the dead middle because, yeah, that's sort of a, a dirtier area where the two forces are mixing, so it's a weaker. That's why the iron filings can go further away from the magnet, is because the strength of the pull is not as strong.
Same thing's happening here at the same time. Now, this is a static field. It's not moving, but...
There we go. That it's only moving in the sense that energy constantly comes in and energy is constantly coming out. So it's not moving like a light bulb is not moving. It's not moving in the sense that the light from a light bulb isn't swirling or turning or doing anything wavy or messy. It's rays of force, straight line rays. And you either hit something with them or you don't. But that's all there is. The ray either hits something, gives it momentum, or it hits something and gets deflected, converted in its direction. And that's all that happens. Nothing else happens to rays of force. They're either absorbed, turned into momentum by the matter, movement, or they're excreted sideways. That's it.
Any interference will travel down these lines in both directions.
Yes, nothing is traveling through those lines, and you can see it if you look at the iron filings. Sometimes the lines are completely broken. There's nothing connecting them. They have huge gaps in them. There's no obligation, there's no current flowing, there's no mechanism flowing, there's nothing flowing through those things. It's just little magnets all lining up in the same direction to create a big magnet. So the iron filings, the little compass needles are all lining up the same way, staggered to each other's side. When they're side by side, they have to be staggered to be attractive. The head of one has to be connected to the tail end of the other. And that's all that's happening. A bunch of heads to tails, heads to tails, heads to tails, heads to tail, and they're lining up, making a magnet, and the new magnet is the exact opposite polarity of the first magnet that made them. And that's all that's happening.
The black travels to here, and the red travels all the way to here. And I said this was the magnetic neutral zone. Okay. Gary didn't like that term, so I'll use it.
I don't care what term you use. I mean, everybody uses all kinds of terms for that middle part, and I don't care which one you use, frankly. Clearly, it's the weakest in terms of they all have the same amount of energy coming out. It's the weakest in terms of its polarity. That is, if you're a magnet, you'll sense it as pretty strong because you can line up black to red. But it's still a little weaker than the top of the magnet for a single charge. So if you had a monopole, that's going to be a weak place because it's going to feel energy from both ends of the magnet. So it's going to be neutralized in terms of its effect. So that's the place. The top end of the magnet and the bottom end of the magnet can affect charges, monopoles, a lot, where the middle of the magnet is really ineffective on monopoles. And again, the field lines are where dipoles line up. So even as a dipole, it's still a little bit weak, you can see, because the lines do bulge out a little bit, which is an indication that the pressure pushing them towards the magnet isn't as strong as it would be if the head was closer to the tail, if you could move the magnets closer together.
And it's the magnetic equalization plane. And
that's a good enough word in the sense that you have an equal amount of black energy and red energy hitting locations that are any distance from that line. So the middle line at a distance, this is where the R cubed thing comes in. Okay, so it's R squared this way. It's R cubed this way. So it gets weak really fast.
Things going on here that a lot of people just don't seem to get. And why it's bowing out at the side is it's because this side here is trying to push away from this.
No. The lines are pushing away from each other because they're all the same polarity, but again, your drawing indicates that they're the same polarity as the main magnet, which they're the opposite. So you have to make these top lines red. And even then, again, focusing on the lines is missing the point. It's rays. Rays, 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 rays. The rays are the force. The lines are just a byproduct. They have nothing to do with the force and its creation. They are just what happens to little magnets when you put them next to a magnet. But they have nothing to do with the function of the light bulb. If I have a light bulb, and it's got a red light bulb on one end and a blue light bulb on the other end, and then I take a photosensitive material, one that's is affected by blue light one way and affected by red light another way, and I put it next to the light bulb, I haven't changed the function of the light bulb by making this piece of paper turn purple, right? The purpleness of the paper isn't saying anything except what the paper's doing. It's not changing the function of the light bulbs. And those field lines are just showing you what compass needles do in the proximity of a magnet. They're not showing you how the magnet functions.
Repel, and unlike charges attract, like down this line. So you've got this force pushing it outwards, pushing the...
So at least you said the word, the force pushing it outwards. Right, so there's no real repulsion and attraction. There's just high pressure and low pressure. Now our vocabulary is going to have a hard time migrating to these new concepts because we're so used to this idea of some sort of magical ability to attract and repel. But it's actually because the repulsion is reflections, so you can think of it in that terms, that reflections automatically increase pressure, mirrors increase photons, or they can just keep bouncing back and forth between the mirror. You can think theoretically. So reflections creates more pressure, no reflection creates less pressure. So there's lots of subtle ways of trying to understand it, but it's all this. Pressure is the key word here. And attraction and repulsion are kind of dangerous terms. You have to be careful about using them. I use them all the time, but I'm just saying the point is that the truth sort of deserves to be more explicit and get to the point, which is reflections create an increase in pressure, and dispersions, relief valves create an absence of pressure. So it's always pushing. You always have to look for what's being pushed into something else. Nothing's ever attracted. Things are always pushed. Something's always pushed.
Out, and I know this. I'm only drawing in the lines of force as illustrative, so we can get a two-dimensional picture of a three-dimensional field. And what I've written down here is...
Again, if you want to look at the field is more like a sun radiating light, or a light bulb. So the straight lines is the better way to represent what the magnet excretes. And we have to understand that it only excretes it because it's coming in from the environment. So it's coming, if I was a magnet, a bunch of red and black stuff mixed is coming into me, and I'm creating an out that's all black on the top and all red on the bottom. And that's what's happening. That's the simple function.
Yes. So you've got all these little charges that are running around doing all sorts of stuff, and I believe all the charges in the universe, well, I believe most of them.
So again, I wouldn't call them charges. I'm clearly, this is another just semantics thing. If we say charges, then we're going to imply that an electron is the same as the energy, okay, that's giving the electron its properties. Clearly, those two things aren't the same. So to call the little bits charged is sort of to, they don't have any little bits between them reflecting. So photons aren't worried about, oh, you're a black photon, I'm a black photon, we have energy between us and we're repelling, and they're not doing any of that. They are the energy. They're the force. So they aren't charged in the sense that they won't behave like a charged particle because there's no force smaller than them pushing them around. So it's dangerous to call the element of what makes something charged the same as what you're calling the charged thing. So I'm just saying it's charged, I think, is just big trouble.
Time are paired. They're paired in a two-charge coupling. So here we've got...
I think you can just use electron force, proton force, because I don't think there's anything else that has this property of charge except electrons and protons.
System here we've got chaos. And later on I'll be doing some experiments where I'm going to be using a 1 kilogram standard, and there's a reason for that. It makes the equations so much simpler. And you know, you guys can
yeah, it makes equations simpler, but 1 kilogram is heavy as fuck, and so, and so it's really hard to have enough energy to move it around. So it's hard to do an experiment with something that weighs that much, because you know, you sort of need, you know, 1,000,000 zilliwatts to move it.
Talk about, oh, it's going to work like this and going to work like that. What about when I start punching numbers in and I start giving you field equations that actually start working out? So I said my little...
Yeah, I love it. I think you can just reduce them, because obviously some of the things that used to be constants and variables that were really not known why they existed, well, now you can know why they exist. So some of it will be, you know, it should be able to take some of those wacky symbols, you know, out of the common math.
Neutron. So that's what I meant by there's more to a neutron than just a proton and electron.
See, I say no, there's nothing more to it. Its function is completely dependent on the electron and proton function. It might as well be an elemental bit, in the sense that that's why it works in an atom. It has kind of a specific role in the atom. I think it's doing one job and one job only, in the sense that it's just allowing protons to get very close to each other.
Interesting thing is the time of stability, and they only give you a mean time, and there are some errors, but it's close enough. You know, the answers they've got there are close enough. So we'll look here and we'll look at what Gary's force bits turn into. It's very interesting, and it also predicts quarks with more than 3 couplings. So you can have particles with 3 quarks, 5 quarks, 7 quarks. Yeah, it's pretty mind-blowing. I think 7's pretty unstable and highly unlikely. So what do we do? Right, here we go, Anne.
So again, I just don't think any of that's integral to the function of atoms in any of the parts that really matter, okay? Like all the chemistry stuff, and you know, we know it's just shared electrons. That's what all the chemistry is really about, is just creating ions and allowing these magnetic systems to have notches on them that are like keys, and they lock together, and you know. So I don't think you need quarks to do any really important physics.
What you get if you got 2 of Gary's force bits straight away, one, we'll call this one the negative. It's arbitrary, and like Gary says, I'll probably pick the wrong, but it doesn't matter. One's positive, one's negative. That's positive, that's negative, and straight away they're drawn to each other.
So right away I'll say no. Force, this can't act on force. All the examples I've given, it's like two electrons interacting with each other. The electrons will never hit each other, because like the ping pong ball example, the ping pong ball starts bouncing so fast and creating so much away pressure that they can't actually hit each other. But the only way the ping pong balls work is the ping pong balls hitting each other wouldn't do anything much. I mean, you could say they could double the force, because they would hit each other and then reflect and hit the surfaces quicker. But I don't think there's any evidence that that's what takes place. And it really wouldn't speed anything up, if you think about it, right? I mean, they're coming at each other. If they reflect off of each other, or they miss each other, missing is going to be just as fast as reflecting off each other, so you really can't increase the energy that way. So force hitting force doesn't work. I mean, if it happens, it can't matter, because the reaction time is the same for the reflection. You could even argue the reflection would be slower, which would mean it'd have less, it would create a reduction in energy, not an increase in energy. So clearly the force bits from one electron, the ping pong balls, have to fly through the space and hit the other electron, and then they have to be re-admitted and hit the other electron. The force has to go to the matter to have an effect. Force on force does nothing. And that fits with all we know about gravity and all we know about charge. That's the original meaning of the word I hate this. You know, symmetry pops into my head in the wrong word. You know, I keep getting all the wrong ones. Superposition. The original definition of superposition was the fact that each force, all right, there's no adding. They can't subtract. That's the word I'm looking for. All they can do is introduce a new force. All you can do is add a force. You can't subtract from a force. So the forces don't interact with each other and then create a new force. They have to actually hit another piece of matter to affect it. So if I have two things and they're shooting energy at a third thing at these angles, they actually have to hit the thing. They can't blend together first and then create a force this way. That doesn't happen. The force bits don't hit each other this way and then create a force this way. They have to hit the matter, and the matter does the math.
Nothing else. If there's nothing else in the local area. So what happens here, if we bring a third one in, right, we bring a third one in here, that'll come into there, that'll come into there, and they'll join there. Now,
see, none of that will happen in my opinion. The forces never combine or stick, as far as I know. There might be some theory that in some circumstance, like in the middle of a sun, you have enough pressure where forces do get so close to each other that they do stick to each other, and then eventually they create an electron. Something like that. But as an interacting body thing, something durable, this doesn't happen. So again, this is all physics where, you know, you can talk about quarks, but we know they don't exist in the sense that they don't last a second. They don't have any life. They don't have any lifespan at all. So why are they part of the conversation in a sense when we know it's like, again, it's like having a conversation about how automobiles work by picking up crash parts, you know, and well, let's talk about this crooked piece of fender. Well, it's not a straight piece of fender. You're not even going to be able to associate it with the original cars. It's so deformed. And this kind of physics is all very deformed from the actual function. So why worry about it? Why play with these broken headlights?
you can get this double coupling here, or what do we get here? We've got 3 of Gary's force bits, and there you go, there's a quark. And here's the opposite, another quark with a different charge. This one we've called plus 2/3, this one we've called minus 2/3. Now,
so I like that this sort of does work, but again, I just don't think it's an important enough feature. But it certainly does indicate that if what they are measuring is just energy, and they're not really measuring a particle, then this fits, in the sense that obviously there's a certain amount of energy going to be released when you break atoms, and that energy can still have pattern to it, because when you're breaking it, the energy was between 2 electrons, let's say, and I pull one of the electrons out. Well, all of a sudden, all the stuff that was bouncing between those 2 electrons is now liberated in one direction. So it'll look like a clump of something, but it's not really a clump.
It's very basic. You know, I've only had a couple of days to think about it and put it into action and see what I got about it. That's what I reckon. I think that's a very...
I guess somebody's got to do that kind of stuff, but again, I just, you know, I'm not saying because I find quarks totally uninteresting that anybody else should find it totally uninteresting. But yeah, I just don't. This stuff is just way too much. You have to make up too much of it. I guess that's all. I'm saying it's a puzzle with so few resolvable surface. You know what I mean? The images have been rubbed off the puzzle pieces so bad that, yeah, you know, you could spend a lifetime trying to make them fit together because there's just so little resolution. You have so little evidence of how to put them together that it's like, why bother?
Yeah, a very interesting view. I've been doing this for, I do sort of weird stuff, doesn't matter. And this is what happens with Gary's particles if they're in a spin. They don't get to join, and they do all this spiraling down.
Yeah, see, there's just nothing to make them do any of that stuff, in my opinion. There's no, it would not be sustainable. They'd always have to be pulled into something in the middle. There would have to be something to keep the spin regular. And again, the whole mechanics of orbits is so subtle. I mean, it's so not durable. Okay, in terms of a little bit of a shake and you screwed the whole thing up. So, I mean, atoms obviously have to be durable. They're created inside of terribly intensely hot and pressurized suns, and yet they survive this transition to the external universe without flying apart. They're clearly a very stable structure, and I just don't think you can have that kind of stability with all this orbity shit.
You can get two chasing each other and get this crazy sort of coupling here. But there are other aspects we need to add in.
I'd certainly argue that neutrons might be spinning as part of their function. Yeah, see, it's basically, as soon as you start spinning something, you have to start moving everything else around, and you just start making a little, you know, a little thing spinning ends up turning it into the whole frickin' galaxy has to start spinning or something. It's just, you know, and then where are you going to get the energy for that?
A lot more aspects. This is what I call the gravitational, electrical, magnetic, mass theory.
Spin theory, yeah.
What was that S for?
S spin. Yeah, no spin necessary. It's I don't know what I've called it, the one force theory or something. The one force theory. It's the only force theory you need. You know, but who knows? Yeah, it's a unification theory fundamentally.
Oh, spin. Yeah, we've got to add. You've got to have spin in the equation. Now, there's already been.
No, I don't. I'd argue there's no fundamental necessary role for it to play. You don't need it.
A million experiments carried out, so there's enough data from most of these experiments for me to be able to analyse them, so I don't have to go out and buy a collider or anything like that. And yeah,
well, you sort of do, unless you trust them, right? Because we really don't get to see exactly what the data is that they base these observations on. We just get, once in a while, get a vague little cloud chamber image, but we don't get to see the apparatus that created it. So, you know, so much of it is, the evidence is not in the courtroom. You know, they just talk about the, you know, well, yeah, we have this piece of evidence, but we're not going to show it to you. You know,
that LHC, you can just about predict every particle that they can manufacture there. They're not stable. They're not worth it.
Well, they're just predicting that they see a pattern and they predict the next iteration in the pattern. But again, they don't know what the pattern is made out of. That the pattern is just the fact that things break down in a certain way. So you could have a pattern for almost anything in terms of how it breaks down. So you could start heating me, and there'd be a certain pattern to the outside surface drying and then it cracking. And there'd be a certain pattern to the heat getting inside and starting to boil the internal parts and liquefy them. You know, there'd be a pattern for what's happening to the flammable elements in terms of them becoming outgassing and becoming flammable and being converted into a fuel for the fire. You know, so there's patterns to how I would degrade. You know, and they're just kind of labeling those patterns, and they're not really. They really have no idea what's causing the pattern. So the patterns of this release of energy, but you know, they're just, and so they're putting a label on it, quark or neutrino or some other bullshit. And I'm just saying, it's saying they know it's a particle when they don't know anything. A particle with no mass. You know what? What's the point of it then? What's, you know, I mean, it doesn't make any sense. I mean, really, just literally doesn't make any sense.
To me, they're just trying to get deeper understanding by spending billions of dollars. And you know, if I was running CERN, I'd be saying, look, oh yeah, there's a big...
Yeah, it'd be really nice if they spent just $1 million. Imagine what they could do with just $1 million on 2 slit experiments and interferometers. If they just spent $1 million on those 2 experiments analyzing what's actually frickin' happening, I think they would learn so much more doing that than, you know, you know, they'd get such a bigger return on investment.
Around the corner, just give me another billion, we'll be right. Yeah, so yeah, there's an unfortunate aspect that you've got to follow the shepherds. You've got to stay with the flock, and I don't buy it. I'll do my own thinking. Thanks. I'll do it independent, and
yeah, but it's a pain in the ass. It's you know, having to convert, you know, idiots and lunatics is hard work. It's a pain in the ass. You know, I shouldn't have to do it. But I mean, you could just argue. I mean, the whole world is just covered with imbeciles who, you know, they actually think there's some fucking spiritual being, you know, somewhere thinking this chaos and waste that we're existing is somehow a necessary pile of crap. Somehow it's okay to just waste all this pain and suffering and allow these things to be torn to pieces. They think that makes sense. I mean, fuck. So yeah, it really sucks having to convert the religious kooks. And physicists are religious kooks. I mean, clearly they've left the grounded evidence building, you know, and are off on a little Jedi adventure, you know, with their little quark swords. Alright, I think that's probably enough for this video. There are other things I could comment on, but I think we'll wait till the next time and such. Not too much in the comment section, I don't think. Let me look real quick, get rid of this, take a look. So the others was holidays. You know, so Superior Mind. I don't think there's anything in here. Great video. Your thoughts on this? Called on-off pattern. Okay. Could these photon patterns be being created, being created by the striking of air molecules and by the photons themselves? So I don't know why. You know, I mean, we've been over it so many times. I'm claiming that surfaces, as we already know, are complex mediums. So when you put 2 different things, air against the skin or air against anything, I mean, water meeting some other incompatible medium, that is, they're chemically not going to mix. They're always complex fields. And we know that with the transparent mediums, those complex fields create reflections off the surfaces, the first surface and the back surface. And we know that depending on the heaviness, whether you're going from a lighter surface to a heavier surface, you'll also create a phase shift. That is, you'll create a timing difference in whatever has to go through this transition of being reflected or refracted. So if it does go through, it'll end up phase shifted when it goes out into the new medium again. So we know it's a process that consumes some time, not only going through the medium, but when it hits this, when it has to actually go through the transition layer, it's obviously hitting something that's slowing it down enough to create a phase shift. It's being translated. It's jumping into a boat and jumping out of another boat, and that takes a little bit of time. Okay, a half phase worth of time or something like that. Well, anyway, we know it's a complex area, so all my arguments happening in this 2 slit experiment is you're pushing light right through the complex area. The whole idea of a small aperture, the aperture getting smaller and smaller and smaller. What does that mean? It means the likelihood that the photon is going near the surface is increasing. That's increasing the likelihood of a diffraction. So why do you find that explanation unsatisfactory? That I have to keep reiterating, well, what's wrong with that explanation? Why don't you tell me what's wrong with that explanation before you keep giving me new alternatives? All right, anyway, let's see. Themselves, who have elastic reflections, that is, conserved velocity but an angled-based reflection when two photons strike each other. So again, this whole idea of two photons striking each other, I think, is just nonsense. The idea that the reflecting surface, like a mirror or some other kind of medium surface that's going to cause an absorption and a readmission, that any one of those surfaces would change depending on how many pieces of light are hitting it, and the surface starts to change, and therefore will change how a new photon will react because it's vibrating the surface. The surface is getting vibrated by each impact, and so any new photon is going to be affected by that vibration. So there can be some mixing of the energy being imposed on the surface. And that could be causing some blending of effect, but it's not really any direct photon hitting photon. I just say that's a non-starter. That will get you nowhere. These reflections would increase exponentially as the as the width slit is decreased. So again, there wouldn't be entirely reflections. We're talking about deflections. We're talking about a photon coming through, hitting an electron. The electron moves a little bit, readmits the photon at a new angle because the electron's at a different position. So there's lots of ways to understand how reflections happen, but pure reflections, that is a photon hitting something and bouncing off, probably don't happen. They always are a U-turn of sorts, some sort of absorption and readmission. These reflections would, okay, we did that. A large number of photons are forced into a complex but small. A large number of photons are forced into a complex but small in width surface area. Again, I don't think it has anything to do. There's the same number of photons. It's just what percentage of the light is being affected. And obviously when a small percentage of the light's being affected, you can't see it. So if you make the hole this big, you're not going to see the little bit of effect that this outer rim is having compared to the brightness of this light. So the brightness of the light will wipe out the effect. As a consequence, the photons going through the slit, well here, the rest that don't go through the slit are absorbed by the material as thermal energy in most cases. Well, that's obviously there's some amount of the photons that hit the surfaces, and don't keep going anywhere. As a consequence, the photons going through the slit, they would be striking each other. No, that just more often as some of them reflect off the complex surface. Nope. This could explain the on-off pattern that we see. It could if you believe that photons can interact with each other when we really have no evidence that they can. So I'm just going to argue I can shoot laser beams at each other all day long, at angle, and I won't get anything going this way. It won't happen. I can't make a photon hit a photon. And even so, regardless, let's see, this could explain the on-off. And even so, regardless of the complexity of the pattern or the appearance of the surface at the atomic level or the electron spin scanning microscope level, well, electrons are working, they're not really using photons. Electron microscope is electrons, so let's not confuse the two subjects, please. The fact that the cannonballs are forced into more reflections may explain the on-off pattern. Again, I think your photon ball replacement theory works great with the above argument. Let me know what you think. I don't think I'm saying photon ball replacement theory. I don't think that's what I'm doing here. Beyond the fact that I'm saying photons are clumps of energy at a distance. But again, photons can't mean anything until they hit an electron. They just can't. They can't do anything. The whole system is dependent on the force hitting the matter. The matter can't do anything without the force to create momentum, and the force can't do anything without the matter to create momentum, to change what the forces are going to, what container the forces are in. If I have one piece of matter in the universe, I change the container that all this force is in by moving it over here. Then all of a sudden, this container is much smaller right here, and this container becomes much bigger just by moving one little atom a distance. I've changed the container that the force is in, so to speak. So physics, stack exchange is a piece of crap. What happens when two photons collide with one another head on, a dead center? Well, obviously that would, again, I've already pointed out, that would be as irrelevant as them missing each other. The above link claims two photons can collide. Well, again, they can claim anything. There's absolutely no experiment, so what can I say? Without an experiment, you got nothing. And if so, the slits forcing them to collide more often could explain the subsequent on-off pattern. Well, again, I think it's bogus. Alright, well, I'll read the rest of this. The next video, I think I'm going to play another two-slit piece of crap from the Royal Institution. So maybe I'll read this when I do that. And such. So, yeah, no slight. It's just a lot of, well, frankly, yeah, the slight is there's just, I propose something, people say, great, and then they describe it completely differently. It's like, I voted for penguins, and they're describing rhinoceroses, It's like, no, penguins. I like rhinoceroses, but no, not for this job. This is a job for a penguin. Alright, that's probably too non sequitur-y. So anyway, okay, so to anyone who is watching this video and has not been here before, yes, I may have made some claims that you think are unsubstantiated, or you don't quite know what they mean, or I can't figure it out. On the channel page, there are playlists, and there are some start here videos and some overview videos that do explain basic concepts of how I have changed physics with a simple idea that gravity is an actual force, and that actual force can also explain magnetism, and that once you understand that that force exists, it can also explain charge and all kinds of other things, and make physics physical again. Yay! So go to the channel page, check out the playlists, and thank you for your attention. Yeah, it's good enough. Alright, hopefully this is a video. Did I remember to start it? I don't even remember if I remember to start it. But we'll find out, won't we? I'll find out. You may not find out.